Yeah, in this video, I'll be talking about how does OSI model actually work in the real world and how actually things pass and what happens and all. We will be taking an example of an HTTPS request, right? And TCP, obviously, because HTTP is TCP. So we're gonna talk about these. This is a topic we can obviously expand on later, and it's need to be expanded later. Actually, I'm not really gonna touch much in depth of TCP, but just things to keep in mind. So okay, for now, this is the request we are gonna call. Okay, it's a post request to this URL, which is http.api.example.user slash then, and it has a message and JSON message which is written over here. We have to transmit over the OSI model. We have to do that. Okay, now first of all, we need to find the IP address of api.example.com because it's just a domain name. It's just a alias, right? api.example.com is an alias. It's not really an address. How do we do that? We first of all try to check in the browser cache if it already exists in there. We can just use the cache and like find its address. If we don't find the cache, we'll go to a router and the router will send it to the ISP, this alias name, and that will go to DNS domain name server, and in within domain name server it will first pass to the .com domain, and then inside a .com domain we'll go to the example, and then in example we'll find API. Then we'll find the actual IP address, which could be anything. Let's say 10.52.4.2 20.5 or whatever it might be, right? It will be a 4 thing. IP address is a topic which we'll obviously expand on later altogether. It's an IP4 address which I've written over here. Off topic, I'll get this in a later video. Okay, we got an address. Let's say we got this IP address. We'll keep it inside, and then overall, we'll just imagine we got an IP address, right? Whatever it might be, we just got that IP address from the user. And when we'll obviously get this IP address, we'll save in the cache so that next time ever we try to hit this URL, we don't have to always go to the ISP and DNS to find it. Okay, we have this IP address. Now our OSI models actually starts in action. First of all, we have our application layer, right? An application layer, which is on our app, on a device, or even in this case, a browser, we create an HTTP request. Okay, it's an HTTP request, right? S secure will happen in the next stage. Don't worry, that will come. The HTTP request will take the message, which is over here, will append a HTTP header and a HTTP request line. Okay, it will append these two things over our message, which is this. Okay, the request line will have the method, the actual IP address, slash message. It should be not user over here, it should be slash. My bad, it should be slash message over here. Okay, right. Within that, this is the URL we are trying to access, the path parameter. Okay, sorry. Now this is the request line and this is our header. It could be anything. We pass our address, IP address in here, and the actual message, right, which is written over here. This is the message, we are going to pass it up ahead. Now this, what is actually happening is we are appending to the data, or I should rather say the HTTP body, which is the message. We are appending our HTTP request header. I should rather write a message over here rather than a data, right? It's a message, it's not a data right now, it's the message which is within our HTTP body, and we will append a HTTP request header on there, which is these two things. We're going to append these two things since we're using HTTP, and this creates this now. Okay, now this thing will be passed to the next layer. Okay, I'll just keep it, and then we have our presentation layer. Presentation layer doesn't really does much, honestly. It is just gonna prepare the HTTP request in there and encrypt it. Since we are using HTTPS secure, we are gonna encrypt it obviously. So that step happens on the presentation layer. Now it will convert into a binary non-readable format so that anyone in middle can't really understand it. Now our data becomes the encrypted version of this thing over here, right? Basically the HTTP request, the message, which is our HTTP body, we will encrypt the whole thing. Okay, we'll encrypt the whole thing and convert it into our data. Now we'll call this whole encrypted thing as data, and this data will be passed to a layer 5, which is session layer. Now, the session layer also doesn't, not directly does anything to the data. It doesn't really touches the data. It creates a secure session establishment using a TLS handshake. Now, once again, TLS handshake is a part of TCP, which we'll be learning somewhere ahead or some other video. What it actually is, it's a part of TCP first of all. We have a client, we have a server. The client goes to the server, says hi. The server says hi, return, and then they just exchange a session key. It's a symmetric key, and it's a topic of totally different to be taken ahead. The main aim of creating a session key is to avoid middleman attack, so that someone cannot fake being a server to the client, and a client can't fake being someone to a server and like act in middle. That is why we have these keys, which we'll be using for actual communication up ahead. Okay, this is the thing which actually happens on our layer 5 session layer. We just do a TLS handshake on session 5. Okay, the data is still data, we haven't touched it. Okay, we have our data now, it's the same thing I've written over here in different color. Now this data will go to the next layer, the transport layer. Okay, the transport layer does the job of breaking into segments. If we were doing UDP, it will be converted into packets, but over right now it will be converted into segments. What is a segment? We take our data, right? I should rather write it like, we have our data which we had over here. It's gonna break it into parts, right? I think that's pretty obvious. We are just gonna break our data into parts. Oh, no. Okay, we're gonna break it into smaller parts, and on each of those parts there might be multiple of them, n number of parts. We will add a TCP header on them. The TCP header is added on the transport layer, a thing to keep in mind. That will now convert each data 1 2 3 4 5 into TCP header plus data 1 data 2 data 3. Okay, what does this TCP header have? This TCP header has the source and destination port, the sequence number. What is this sequence number? This is basically the data 1, data 2, data 3 sequence number. That the first, this is data, this is data, this is data, the sequence number. Why do we append this sequence number? Because while sending the data, what can happen is we can first get the data 3 or else a sequence number 3 first, right? We can get the 3, we can get the 2 for then, and then we can get the 1, and then we can get the 4. It can happen because while transmitting there might be some reason and some data being up and down can happen. So when the server side gets this data, it knows that okay, first I need to read the 1, then I need to read the 2, and then the 3, and then the 4. That is the main goal of adding this sequence number. That's it, to make sure that the sequence is correct while receiving the data over there. The acknowledgement number, this is once again the part of TCP, three-way handshake and stuff, the sync flag, the async flag. This will come under when we learn the TCP. Then a checksum to make sure if the data is which we have received is correct and there haven't been any mistake in there. That is also something to be learned while learning TCP, not right now. Now we had a data, now it has been converted to TCP segment. The difference between a data and a TCP segment is we just add a header on there. That's it. Now it becomes a TCP segment. Now this TCP segment will be passed on to the next layer, which is the network layer. The network layer will take the TCP header plus data, which comes from the transport layer, and just convert it into this thing. Now this thing just is the same thing, just we are adding an IP header to it. Now what does the IP header hold? A source IP and destination IP. That's it. We are just going to take this whole thing which was created over here, we are just going to append this header to it, and this becomes the same thing. Now we call this an IP datagram. A difference between a TCP segment and an IP datagram is that we are just adding an IP header to it. That's pretty much it. The source IP and the destination IP headers. Okay. Now this IP datagram, which is basically an IP header plus a TCP header plus data 1 or data 2, data 3, that whatever that might be, the segment of it, that whole thing will be passed to the next layer of data link. This whole thing, which is over here, exactly word to word, we are just going to add a MAC header to it now. MAC header has the source MAC address, which is our device in this case, and the destination MAC address, which is the address of a router. What is a MAC address? It is nothing more than just an unique address or number given to each devices in a system. Whenever you buy a PC or a phone or a mobile phone or a router or anything might be which works on a network, it comes in with a predefined MAC address on it. Okay, it is not changeable, it is fixed whenever you buy a device. Okay, obviously you can look into MAC address later, that's a topic. I mean, it's not really much to get into. So this MAC header just has a source MAC address and a destination MAC address. This whole thing is called a frame now. Okay, now this frame is passed to the physical layer, and now this frame just gets converted into actually physical data, which is bits, zeros and one. If we are passing the data electrically using an axial cable, this will just be 0 1 0 1 0 1 formatted data that's gonna be passed, right? It will be converted into electricity basically. If you are using axial, it will be converted into electricity, the frame. If you are using let's say our light one, which is what do we use, light data transfer, called not light, photons. Fiber optics, yeah, there we go. If you're using fiber optics, it will be converted into photons. Okay, I don't know the spelling of photons. So if you're using an axial cable, it will be converted into electricity. If you're using fiber optics, it will convert into photons. Now this photons will actually reach our server, and now once again reaching our server, I'll just show this frame got converted into bits. Now these are actual physical things. I'll just reiterate once again what happened so far. Okay, we had a request to make. We got its IP address by asking a router or the cache or going to a DNS and finding it out. We found the IP address. Now the actual layer starts. We take the go to the application. It creates a HTTP request. It takes a message. Okay, it took our message. It added these things over here, which are called these two things added on it, which is our request header plus message. So it converts and becomes this. Now this whole thing is passed to the presentation layer, which prepares it in the sense that formats it a little bit and encrypts it mainly, and that encryption converts it into non-readable format, and now this encrypted thing will call it data. Now this data goes to a session layer. The session layer just establishes a connection between the server and the present user using TLS handshake. The TLS handshake is nothing more than just client and server saying hi to each other and then just sharing each other the session key. This session key is required for identifying the other person in the network. That's it. Where were we? Now we got the data. We take this data, we go to a transport layer. It is breaking into segments, data 1, data 3. On each of this data, we'll append a TCP header. The TCP header has these things, right? And now each of these things are called a TCP segment. This TCP segment goes to a network layer. The TCP header and data 1 is now appended with the IP header. This IP header has the source destination and the source and destination IP. Now we call it a data IP datagram. This IPgram goes to data link. Data link appends a MAC address. This MAC address is just the source and the device, and device to the router. And now actually officially on the data link layer, we officially send our message from the device to the router now, right? And now on physical layer, in the sense like they just get transferred on these two layer mainly. This layer just start happening all on our devices. These two layers are actually when we are transferring things ahead, right? Now it will receive to the server, the server gets the bits, it will decipher, convert into these things, which is the MAC address it has to go to, the IP header, the TCP header, data 1. Now that will pass ahead, we'll decipher the destination within the server, the destination of the IP, we'll open the header, the TCP header, we'll figure out its sequence number and those things, and then we open it totally and we get the data now. Now the server sees the data, unencrypts it, able to see the data, and the server will see this message now. Pretty much it. Overall, that is how it all works. There is something NAT which I haven't really talked about, but NAT is something which can be done in a totally different topic, which happens over years. But that doesn't really appear, isn't really a concept of OSI model, so that will happen some other day. Okay. Um, Thank you.